So for our step one in our area approximation, we broke up the x-axis into 4 equal pieces. There's nothing magical about 4. We just decided that it was a nice number of rectangles. And so now you need to choose a sample point from each of the subintervals. And remember, the subintervals, here's one of the little subintervals, here's another one, here's another one. What am I saying with this xi plus 1? I'm describing a general subinterval. I don't know which one you're picking. Maybe you pick that one, or maybe you pick this one. And I'm saying, okay, the ith subinterval, I goes from 1, 2, 3, 4, allows you to pick a point, a test point. And so a couple of comments here on these test points. So first comment is the sample point can be, they could be all left endpoints. They could be all right endpoints. They could be all midpoints of each interval, or they could be all random. But of course, when I say random, I do mean a random point from each subinterval, right? You do have to pick the point in the little piece of the x-axis that you're working at. Let's point out that your choice of your sample points, it does affect the estimate. So when you're estimating the area, if you pick left endpoints and I pick right endpoints, we're going to get different estimates. But we're going to be able to take this technique and actually compute precise area. And it's not going to affect I'll just say the precise area. You know what, let's say the actual area. Somehow that's obvious, but what I'm saying is it's not going to affect how we compute the actual area. Even though the estimate's off, as our estimates gets finer and finer and finer, we're going to be able to get the exact area, even if your estimate is different. So, okay, so what's next? Well, let's point out to you that when you've picked your test point, let's pick a test point right here. I picked this test point. I plug it into my function, and now that's the height of my rectangle. And so here I get this rectangle. I need the area of that rectangle. And what I want you to realize is the area of the rectangle is the base times the height. The base is always just delta x. So the area, let's actually say this, the area of each little rectangle is delta x times f of your test point. And this xi star is just the test point that you're plugging in, and that's what you get. So we're going to do that in our example. Let's actually do right endpoints, left endpoints, and midpoints in our example. So I've gone ahead and worked these out for you. So thinking about our area here, I'm going to erase this one and actually copy in the last one that we had, pardon me. Let's just erase this, delete, delete, and then we can copy. I think I've got it. There it is. Okay. All right, so if I want to work with right endpoints, then I'm going to go 1/4. Right, here's a right endpoint, 1/4, 2/4, 3/4, and 1. Those are my right endpoints. If I'm going to go left endpoints, I'm going to go left endpoint 0, 1/4, 2/4, and 3/4. Notice a lot of these are either 1, but when you're taking right endpoints, you don't get 0, you do get 1 as a right endpoint. Left endpoints, you do get 0, but not 1 over here. Okay, midpoints. The first midpoint is going to be an 1/8, and then 3/8, and then 5/8, and then 7/8. So just showing you how you can pick sample points. You could pick random ones in each little interval. Doesn't matter. Let's actually work out the area estimates for each one. So if I want to use right endpoints, we typically denote that. I'm using 4. So I would denote the area estimate with 4 right endpoints as r sub 4. And let's just work through it. We know that the width of each little piece, delta x, is 1/4. So for the right endpoints, first one, I'm going to get 1/4. I'm plugging the right endpoint into my function. So I'm plugging in this right endpoint 1/4 into f. So it's 1/4 times f of 1/4. That's the first rectangle right here. Okay, then I'm going to plug in this one, then I'm going to plug in this one, then I'm going to plug in this one. That's what we're actually computing right there. So I get 1/4. This is delta x times fxi star. Now I'm going to say plus the next rectangle, this guy right here, is going to be, again, width is 1/4, height is plug in 2/4. Next rectangle, this guy right here, is going to be width 1/4, plug in f of 3/4. And then finally, width 1/4, plug in f of 1. Remember, f of x is just x squared, so this isn't too bad to compute. You can actually factor the 1/4 out, and you get just f of 1/4. So it's going to be this 1/4, 1/4, 1/4, 1/4. I factored out, and now I can say f of 1/4 is 1/16. You just square plus 1/2 squared is, well, let's just say it like this. So 2/4 squared is 4/16 plus 9/16 plus 1. And when you work this out, you end up with 15/32. So that's our first area estimate, is 15/32. Let's go ahead and get a numerical approximation. Oops, I've got my calculator here. 15 divided by 32. And I get this is roughly 0.4687. So that's our first estimate. Now let's go through and let's estimate with the left endpoints. So I'm going to actually erase this picture. Let's just erase this. And then we'll do it again now with left endpoints. Okay, so left endpoints, you're going to plug 0 in. And well, when you plug in 0, you actually get out 0. So again, left endpoints, we're going to write L sub 4 for the area estimate with 4 endpoints, and we're going to get 1/4. F of the left endpoint is 0. That's this first rectangle right here. Then the next one, we're going to plug in left endpoint is 1/4, and then we're going to say times the width. So 1/4 times f of 1/4 plus 1/4 times f of, looking up here, our left endpoints, just going through, 1/4 f of 2/4 plus 1/4 f of 3/4. And I'll let you work out the details, but you can actually estimate this, and you're going to get 7/32, which is quite a bit smaller. And you can see we're underestimating everywhere. When we use left endpoints, we're underestimating. So our right endpoints gave us an overestimate. Our left endpoints gave us an underestimate. I have 7/32. Let's just approximate that. 7 divided by 32. This is roughly 0.21. Let's say 2187. And so if we wanted to, we could actually average these two. We could say, okay, if you average the left and the right endpoints, we're going to get somewhere around 0.3 is our area. For the midpoint, we usually write that M4. And again, it's 1/4 times f of, plug in each of these midpoints. So f of 1/8 plus 1/4 times f of 3/8 plus 1/4 times f of 5/8 plus 1/4 times f of 7/8. And I would like you guys to work it out, keeping in mind f of x is just x squared, and I came up with 21/64. So that's how you estimate the area. This is a little bit technical, I realize that, and some of you are probably looking at this wondering how much is he going to make us do this. Well, good news, I'm not actually going to make you do really any of these kinds of problems. Typically I ask for 1 or 2 in the homework, but I'm going to waive those. What I'm going with this is I want you to understand the ideas behind what we are going to do. We're going to develop some theory that's going to allow us to compute precise areas without having to do these estimations. And so the next video, I'm going to bridge that gap with you. I'm going to show you how we can compute it precisely, and then we're going to begin to see some techniques that we can use. So let's go to the next video, and we'll actually work out the exact area instead of just